in the next number of days, we try to, so that the crop can use it in the next number of days, and then we irrigate again. So the question is, how do we know then when to irrigate and how much water to add? How much discharge of water, rate of application are we going to have? Remember, initially, when we were calculating or when we were doing our calculations, we also saw that in addition to that water for evapotranspiration, you need to provide water for that is expected to be lost through irrigation, the various irrigation application methods. For example, the water that is lost is the water is running through the distribution system of the irrigation and so forth and so on. For example, when the water comes from a river and it is being transported through an earthen canal all the way into your irrigation scheme, you can have evaporation losses, you can have deep percolation or infiltration losses which lead to deep percolation, and so you also have to add that water in the amount of water that you are supplying, or you have to store for the purposes of that particular irrigation. So now the question is, how do you determine when and how much to irrigate? So generally, how do you determine the timing and depth of future irrigations? One, remember, and I'm just kind of trying to remind ourselves what we learned in irrigation and drainage engineering 1. When the moisture content in the root zone falls below critical moisture content, then your crop starts to encounter stress, and the evapotranspiration from that crop after that condition is going to be, it is going to fall below actual evapotranspiration. Your crop will start to encounter water stress. And finally, the yield that you are going to attain is going to be less than 100% yield. Of course, let me mention here, most of the times the objective of irrigation, and even when you talk to agriculturists, agricultural engineers, attaining 100% yield from a crop is damn expensive. And sometimes when you do cost-benefit analysis, it may be prudent, or it may be beneficial to allow a little bit of stress. But for irrigation engineering, from the point of view of a civil engineer, we want to provide a system that can provide enough water to attain maximum yield. So, if we are not supposed to allow the water to fall below critical moisture content, how do we calculate critical moisture content? When you recall, it is the fraction P, or depletion factor P, multiplied by the difference between moisture content at field capacity and moisture content at permanent wilting point. So the objective then is to irrigate when the moisture is still does not or has not fallen before moisture content at critical moisture content. That is number 1. 2, we also do not want to add so much water so that the water goes above moisture content at field capacity. What does that mean? What is moisture content at field capacity? And just to remind ourselves, moisture content at field capacity is that moisture which is held by the soil matrix against gravity. What do we mean by that? It is that moisture that is held against gravity. This is what it means. Imagine you have a sponge and a basin of water. Then you dip this sponge in that basin of water. A sponge is like a soil matrix. It has pores. It has a network of solids. and you find that in between we have air when it is dry. When it is wet or it has some moisture, you are going to have air and some moisture. So I can use that as a kind of an example of a soil matrix. So when you dip that sponge in a basin and fully, what you will see, you are going to see the bubbles that are in the pore spaces of that sponge come out, and at some point that sponge is going to be fully saturated with water. So we could say the moisture content of that sponge at that point is moisture content at saturation, or saturation moisture content, which is usually equal to porosity. Now, if you lift that sponge and imagine you are not squeezing it, you are not applying any external pressure on it, if you can be able to do that. So lift it by the tip of a finger. Water is going to flow out. Water is going to flow out of the sponge through gravity. So the water is going to drip out through gravity, and a point is going to be reached where no more water falls out of the sponge. You are not adding any pressure. At that point, the sponge will still be heavy. It will still have a lot of water in it, and that water is held by the sponge against gravity. It is not flowing out. For it to be released, you have to squeeze the sponge. So moisture content at field capacity is that point where the water in the soil matrix is held against gravity. At that point, and you could say it is the maximum water holding capacity of a soil. Why? Because if you add more water into that soil matrix, beyond moisture content at full capacity, you are going to the water is going to flow away through gravity and probably recharge groundwater into deeper. It will percolate into deeper horizons of the soil. So in irrigation, we do not want to add more water in the soil beyond full capacity. Why? Because excess water is going to be lost, and we do not want to the moisture content to fall below critical moisture content, because actual evapotranspiration is going to fall below evapotranspiration under standard conditions, and that will lead to reduced yields. So that now we can get ourselves into this irrigation scheduling properly, we are going to define a number of a number of terms that are commonly used here, and I think I've already talked about them. We have root zone depletion, and that is the shortage of water in the root zone with its maximum water holding capacity. And I've already said that is the field capacity. So if we have irrigated today the soil up to field capacity, and the water is crops use water today, tomorrow the moisture content is going to fall. So that deficit from the moisture content at field capacity, that is what we call root zone depletion. So anytime we are irrigating, we want to fill that depletion. So if, let's say today, from yesterday, the field capacity was, let's say 30 volume percent, and then today it is let's say 14 millimeters of water, 30 millimeters of water, and today it is 14 millimeters of water. So when we're irrigating, we want to add 16 millimeters so that we can fill that. So that is, and the root zone depletion will be 16. What is the maximum depletion? There is a maximum depletion, and it is also called the maximum allowable root zone depletion, is the maximum amount of water that a crop can extract from the soil without suffering water stress. That is, then the moisture content, or the moisture between field capacity and critical moisture content. And it is also usually called the readily available moisture. It is also usually called the readily available moisture. So if we were to calculate the maximum depletion, you would get theta FC minus P minus or rather it will be P into brackets theta FC minus theta PWP. And then you will multiply by 10 in order to convert that moisture content by volume basis into millimeters. So it is P theta FP minus theta PWP, and you put it into brackets. Then we have water application depth, which is also denoted as DA. And now these are terms that you have not seen before, but now you are going to see them because it is irrigation. Sorry, you have seen them in irrigation scheduling before, but it only in soil water plant relationships were not introduced, but now you see them here. Now, in our calculations of evapotranspiration, you noticed we did it in terms of millimeters. And there is a way to convert these millimeters of water into volumes. There is a way to convert moisture content by mass basis into volume basis from soil mechanics. But now in irrigation, when we are talking about application depths, it is easier. Reason why? Because we calculate them in millimeters, in linear units, because that one is easier. Now, for starters, if you remember, during the soil-water plant relationships, each particular soil has a specific characteristic when it comes to the water holding capacity, the theta FC and the theta PWP. And then each crop has a specific value P, that is the depletion factor. Factor P. Each soil has such kind of a unit. Oh, no, each crop. So every soil has specific water holding capacity. Now, if let's say, and I've already explained that, if today, if for a particular given time step I, the moisture content is equals to a certain value theta I, then the maximum water application depth is equal to the root zone depletion. And I've already explained what the root zone depletion is. It is theta FC minus the moisture content at that particular at that particular moment. So that, and then you remember how to calculate a depth of water or equivalent depth of water. It is usually 10 theta. And if you want to calculate the amount of depth of water for a particular depth of soil, you multiply with root zone depth Z. So the dA is usually given by 10 multiplied by theta FC minus theta I times Z. Now, the maximum dA, maximum depletion or maximum water application depth that you can ever think of, the theta I will be theta PWP, and then you have to multiply by the factor P. Now, if, and I think I've already explained that, I think I'm really running away. So I've already said maximum depletion will be readily available moisture, which is PZ times SA. SA is equivalent depth of water, and it is usually denoted by multiplying theta by 10. And then Z is the depth of the root zone or the root zone depth. For a bean crop, it will be different. For a maize crop, it will be different. And these typical values are provided. And where do we find this kind of information? We find this kind of information, most of these things, in FAO irrigation and drainage papers. Now, if you are the net depth of application, you just get P times Z times SA. And then if you're talking about gross, you can now think about the application efficiency. Divide the readily available moisture by the application efficiency. When you are thinking also again about the application depths, water application depths, you have to think about the various irrigation methods and their typical application depths. Surface irrigation systems can apply very high depths of water, especially the basin irrigation and the border strip irrigation system. Drip irrigation, furrow irrigation, not so much. Sprinkler irrigation also can apply quite high irrigation depths. Now, why is this relevant? Because number one, if you have a bean crop whose root zone depth is 30 millimeters, 1 foot, then why would you use a basin irrigation depth, which is going to apply water depth from 50 millimeters and more? Because the excess 20 millimeters is just lost through deep percolation. Two, if you have a maize crop, then imagine drip irrigation 10 to 30 meters. And if that maize crop has a root zone depth of 1.5 meters, for example. Of course, I'm just giving arbitrary values. So when selecting a method of application or a particular application depth, you have to think the various irrigation methods and their typical values of water application. Then we have water application duration. So if you want to apply 100 millimeters of water and your stream size or your discharge or your supply is applying at a certain rate discharge, how long are you going to take to apply that application depth? And before I go there, I think there's something I forgot to mention. Irrigation interval, that one, I will explain it later, I think. So the water application duration is basically, if I start my water application, I start irrigating now, how long should it take me to apply the desired water application depth? It is usually denoted as WAD. You look at literature, you'll find that that is called WAD. In literature, RAM can also be called readily available water, so you may find it called RAW. Then in soil water plant relationships, you also call total available moisture, which it can also be called total available water. Okay, so the water application duration is usually given by 10,000, which is just a conversion factor, multiply depth of application that you have, whether it is maximum water application depth or it is just, like what we have seen, if the moisture content is not critical, then multiply by your area in hectares, then divide by your stream in liters per second. Then 10,000 is just a conversion factor. Of course, if you do not want to use a conversion factor, you can use dA times AU multiplied by QU, but make the units consistent. This 10,000 is used with the units as I have given up here. Otherwise, you are going to have to make the units consistent yourself. So what is QU? QU is called the unit flow. And basically it is the discharge. Let's say you have designed your system and you have seen, I will design a pipe that delivers 5 liters per second. I'm going to design a pipe that delivers 10 liters per second. That is the QU. What is the water then we have the water application time and irrigation interval. So first, you want to know when to irrigate. So if I've irrigated today, I've started my irrigation today. When do I irrigate next? And then we have the irrigation interval. So the irrigation time is when you start to irrigate. So let me just draw something here. So let us say I have started to irrigate today, and we have so many days. So I've started my irrigation today at that point. Your kitu hii. So let me just draw a new one. Okay, these people. So I've started to irrigate at that point today, and my irrigation takes let's say 8 hours. It has taken 8 hours up to that point. And then my irrigation interval starts from the start of the water application from today all the way up to the irrigation interval will be up to a certain point, let's say there, so that the irrigation duration is part of the irrigation interval. So see where our irrigation interval starts and ends, so that the next irrigation time is going to be at the end of the irrigation interval, and the irrigation duration forms part or is a subset of the irrigation interval. So the time between, let me delete these things. It's not like the Kenneth of before. This one has become a little bit more complex for me. So the time between successive water applications is called irrigation interval and is measured from, and I've already illustrated that, the start of one water application to the start of the next water application, and therefore includes the water application duration. It is usually expressed in seconds, but normally you can have it in terms of hours, days, decades. A decade is a 10-day period. So you can express it based on the units that you have for, number one, for your net irrigation or your readily available moisture, or your evapotranspiration. Is it millimeters per day? Is it millimeters per whatever? So it depends on the units that you use. So you, at the end of the day, the irrigation interval is expressed in terms of time. For optimum water supply, if you want to optimize your system, you should not allow, and I've stated before, that your water goes below maximum depletion. That is, you should not allow depletion more than readily available moisture. And if I may ask, and if you want to respond, you can unmute yourself. What is this readily available moisture according to our what we have defined? What is the readily available moisture? You can unmute so that we can proceed, because I have really talked about it a lot. And I can even see it, I can see it on the screen. What is the readily available moisture? And the reason why I'm calling us to join with microphones is so that we may respond. And I said before, I stated last week, I do not have to teach you. You can always say we need a different teacher, because for me, if there's no interaction, we are not going to learn. We have to. And Tevin, Braddon, and Totona, you are going to be kicked out of the meeting because you have joined with call options. So I'm going to remove you just immediately, both of you. So I'm asking a question and I'm requesting a response. The question is, what is readily available moisture?
Well, I think the readily available moisture is the moisture between the field capacity and the critical moisture content.
Thank you, Kamau, because that is exactly what we are talking about. And if you look at this, that is what I have explained. You have to get, it is the, it is the theta FC minus P depletion factor minus theta FC minus theta depletion. So that is the maximum depletion. Then, yeah, so I was talking about the optimum. When if you want to optimize your system, you need to not allow your moisture content to fall below readily available moisture. So you see and you notice soil moisture is a great determinant. Soil moisture is a great determinant of how much water or the water application time when we apply the moisture determines is a great, is dependent on the amount of moisture in our soil. We have very many ways of timing water applications times, but we'll see them a little bit later. But first, let us look at the basis of calculating irrigation intervals. If we have the previous interval or the current irrigation interval being I, or the previous water application time, or the current time being I and the previous water application time being I minus 1, then the moisture content during that previous time will be theta I minus 1. And remember, I have been saying that you need to fill your soil moisture content to full capacity. Beyond that, the excess water is going to flow away through gravity. But remember, you can sometimes even apply some water and it does not reach full capacity, but just it is above theta FC. So let's say you irrigate your, after irrigating, your moisture content was theta I minus 1. If the IN, which is the net irrigation requirement, is the average net irrigation required for interval I, and I will ask another question, but let me finish this. Then the maximum duration in days is given by, this is how you calculate interval. Interval for this particular duration I, the current one, will be theta I minus 1 minus theta I, multiply by 10, just a conversion factor, then divide by net irrigation requirement. Now, I want to ask a question. How do we calculate net irrigation requirement? How do we calculate net irrigation requirement? We have to remember, I wonder whether you did it last semester or last semester, but one. And that is why when I saw this irrigation scheduling being put together with irrigation and drainage 2, I wondered because it goes very well with irrigation and drainage engineering 1, because IN is calculated, then we have a lot of theta FC, theta PWP, theta, we have PZ, and so O and SA, all these things are very much in irrigation and drainage engineering 1 under the soil water plant relationship. So the question is, how do we calculate net irrigation requirement? And that is from your last class, and I will post the question on the WhatsApp group so that we can respond. How do we, you can respond net irrigation requirement IN. So we can respond this later. I will not answer. You will have to go to your either the crop water requirement calculations, irrigation water requirement calculation, and soil water plant relationships calculations. So, and I've given a very small example here, which you can follow at your, it's just application of what we have here. And then when you are going back to your notes, try to look at the meaning of SA, that is the equivalent depth of water, look at the meaning of P, look at the meaning of Z, look at the meaning of I, and look at the meaning of all this, so that we can now bring ourselves back. We can refresh our memories about this. So I have, the problem is fully solved, and you can follow it, and if there is a question, ask. So of course, we did not have this science in the past. Even currently, sometimes it may not be very practical, and especially for most of us who usually do small-scale irrigation, and there is usually some methods that farmers use, some, you can call them rough methods that farmers use in order to determine irrigation scheduling. And one of them is plant observation. When you see plants are lazy, for example, you see, such kind of things. You say, or you look at your soil, you see it is drying out, and then you say, no, I need to irrigate. This plant of the observation is one of the ancient irrigation scheduling method of irrigation scheduling. So you just irrigate when you see your crops have encountered stress, but it has a downside, because one, if you see the crops are lazy, sometimes the crops are lazy, but there's a lot of moisture in the ground, especially during the dry season. No, the wet season, when there's a lot of moisture in the ground, but the sun, remember again, it is usually too hot. The sun is usually, it is usually strange in a way. During that time, you may find your crops look lazy, but there's still a lot of moisture. So you may end up adding more water into the soil unnecessarily. And then again, for example, if you see your leaves are curling, for example, maize leaves starts to turn like needles, most of the time at that point, the moisture content is below critical moisture content. So we have nowadays more methods of doing this scheduling, and under this category, we are calling what we call it real-time scheduling. So you can have soil moisture meters, whereby you install moisture measurements in the soil, and then you will be measuring like every day, what is the moisture content, has it gotten to the critical moisture content, and so forth and so on. But how practical is that? You need a lot of manpower and also resources so that you can be able to do that. Of course, we have some gadgets like tensiometers, electric resistance blocks, we have neutron probes, and the other method of measurement is like the gravimetric method, whereby you get a sample of soil in the field, go oven dry it for 24 hours. Remember, when you are doing that oven drying, your crop is using more water. So, you have like a one day time delay. So you can go, by the time you're determining, the moisture content is falling below critical moisture content, it will be a day later. So you can use this kind of real-time scheduling, but the question is, or rather, not really the question, but just to make a comment. I had a student who wanted to do a project to do irrigation scheduling, a gadget, this Internet of Things kind of a thing for real-time scheduling. And for you to be able to do such kind of an app, he wanted to develop an app so that you can do some Internet of Things. You just get a notification on your phone that tells you need to go irrigate, it is dry. And using these gadgets like tensiometers, especially and the neutron moisture probes, because those ones, the ones that are in the market, produce a record that you can read. You can always, relay that record into some kind of these things, and then you can develop such kind of a gadget. So for those of you who are interested in programming, this is an area where you can easily capitalize on for small scale farmers. So I've talked about the tensiometers. I don't think I taught you irrigation, but you can, I would know hydrology one. So I taught tensiometers, things of measuring moisture content. You can find them either there or in soil mechanics, but you can just read a little bit about those methods. Then we have cumulative pan evaporation. So you have a pan evaporator in your field, in your irrigation scheme, and then you are able to record, you are able to determine the open water evaporation, which you can change into ET crop. Then we have the soil water budget, whereby a special case is use of the lysimeters. And that one, you should have also seen it in irrigation and drainage engineering one, how to measure soil water using the soil water budget method. But we have those methods, like I've said, may be a little bit tricky because of the level of involvement that is needed. The practical methods of irrigation, number one, and I want us to take a break, and when we come back, we are going to come and continue with them. Of course, we are almost finishing things, so we will take a break, and then when we come back, we are going to continue with this. Any question? And I encourage us to ask questions, even if it's to just make a comment, ask a question. In the meantime, I'm going to post a poll and see who is with us and who is not with us. So once you respond with whichever way, I will know whether you are present or absent. So for example, Elvis Karumbi, Emma Grace Owino, Fidel William Wako, Elvis Karumbi, Emma Grace Owino, and William Wako. Those people are just here to take us for a ride. And I explained before, you better not attend my class than to attend just for the sake of being seen. Because those three people, the next time I come, I call a new call, and I usually do my calls anytime, and you're not in, I will kick you out of the meeting. Elvis Karumbi, Emma Grace Owino, and William Wako, you are going to leave the class. Let us take about 10 to 15 minutes, and when we come back, we will continue with real-time. We will continue with real-time or practical irrigation scheduling. So we continue with practical irrigation schedules. And why is this important? Remember, when we were learning crop water requirement, we learned that at different stages of crop growth, um, the crop water requirement is different. Can anyone remind me why? Or maybe we can even start with what are the various crop development stages? And now I'm going to take this opportunity. I will take another poll so that I see who is in, and I'm going to save my attendance at this point. Let me take another poll. Then I'm going to save attendance for today. So Elvis Karumbi, Gilbert Shibega, Melvin Anthony Kinoti, Violeta Koth. So these three people are not present, so they have to be removed before I save. So we have Elvis Karumbi. He is supposed to be remove user.